Hi, so welcome back. So in this lecture, we will learn about variance and standard deviation, which is connected to expectation, which we have already learned before. But it's taking the idea of measuring a population or understanding the values that are distributed in a population a little bit more. And that's what variance gives us. So we'll start with x being a random variable, of course, and the average or expectation of x is m. The average, of course, is the average values that x can take. Okay, so that is expectation, which is m. We've already introduced that notation before. The way we define variance for this random variable x is by expectation of the square of the difference of a value of x, for example, from the average value. Okay, so this is a new quantity here whose expectation which we have to find, and that value and whatever this comes to, that is called the variance of x. Okay, so again, it's measuring how much x is differing, a value of x is differing from the average value. We're taking the square of that. This is a new random variable. Okay. If you want, this can be written as a random variable z, for example. If I write z to be this random variable, which is made out of x minus the average value square. If I call this new thing z, of course, as x takes different values, z will take different values. So z will have its own spectrum and it will be a random variable. So this, it basically variance of x means we have to find the expectation of this new random variable, which is made out of the old random variable x. Okay, and the way this works out is in formula. Or the way this works out is, of course, if x is a discrete random variable, then the expectation will be calculated as each value of this new random variable z, which is the individual values of x minus the average value square, okay, which will be the individual values of z. If x takes the individual values xi's, then z will take the individual values xi minus m square, multiplied by the PDF, or the PMF, sorry, because we're dealing with the discrete random variable. So the PMF of the variable x, which is probability that x takes the value xi, this whole thing worked out over, or the summation is taken over the entire spectrum of x. Okay, just as expectation, if you remember, expectation of x was just xi, then PMF x equals xi. Okay, the probability x equals xi, and similarly we'll work out this expectation of this new random variable by each values of this new random variable multiplied by the PMF of x. Okay. Similarly, if it's a continuous random variable, PMFs will be replaced by PDFs. So that p x equals xi will be replaced by the PDF f, for example, small f, and individual summations will be, or discrete summation will be replaced by continuous summation, which is integration from minus infinity to plus infinity, and discrete values of zi's will be replaced by continuous values of zi, which is x minus m square. Okay, so that will be the in formula, this will be the definition of the variance of x. Okay, now there's one thing that we must mention here. I've written the word lotus here, over here, for a reason. The thing is, so I'll just rub this out. We'll just write something here. If variance means finding the expectation of this new random variable z, because this is z. Technically speaking, think of x as a discrete random variable, then z is also a discrete random variable. Technically speaking, the expectation of this, or expectation of z, will be summation zi's and the PMF of Z, which should be different from the PMF of X. If Z is a different random variable than X, then it should get its own PMF. And it does, okay? If you change the random variable, if they're not the same random variables, then they must have different PMFs, okay? And of course, these will be, the summation will be over the spectrum of Z, okay? And this will be, technically speaking, this will be the variance of X, okay? Because this is that, okay? So these two formulas here, they don't match. If I go by the technicalities of this, finding the expectation of this quantity Z should be this formula and not this formula. You should have a PMF of Z and not a PMF of X here, okay? Remember, this is Zi. This whole thing is Zi, okay? So what's the problem here? I mean, why are we not taking this in the formula but taking this? Because the two sums come out to be the same, okay? And that's what I refer to as lotus, okay? The full form of lotus is the law of the unconscious statistician, okay? If you take expectation of two random variables which are different but connected in a form like this, okay, then if you unconsciously, if you don't follow the technicalities of it, even if you don't write the PMF of Z but unconsciously write the PMF of X, then even then the two sums work out to be the same, okay? That's the same case with the continuous random variable as well, okay? You should be, technically speaking, should be using the PDF of Z and not the PDF of X, but again, the two sums or the two integrations in this case, when X is continuous, they will come out to be the same, and so the formula works here, okay? And that's why we don't complicate things. We just keep, because knowing X means we already know the PDF or the PMF of X, we just write this as the formula, and this comes out to be what the answer should be, okay? We can spend some more time or a different lecture on this lotus and why the two sums come out to be the same, but that's for later. But you can trust me for now that this formula will work and the answers will be right, okay? So that's the variance, that's in formula for the two different cases when X is discrete and continuous. Now, this can actually be written, if you work this out, this has a smaller or an easier formula, okay? Sometimes this is easier, sometimes that is easier, depends, okay? But really, if you just work this out, I'll just work this out here. I'll explain this part here and then I'll rub it out. But so this if you work this out, expectation of x minus m whole square, this is expectation of x square plus m square minus 2m capital X. By linearity of expectation, you can take individual expectations. So you will have expectation of x square plus expectation of m square, but m square is a constant, so that remains m square, okay? Expectation of a constant random variable is constant, okay? It's the same constant actually. Minus 2m expectation of x, again, expectation of minus 2mx, minus 2m is the constant, and this was there in the property of expectation when we had learned expectation. You can take out the constant, which is minus 2m, and you're left with this. You get m from this, because expectation of x is m, okay? So you have m square minus 2m square, which gives you, this whole thing gives you a minus m square, and therefore you have this formula, okay? This one is this, and these two will work out to give you a minus m square, and therefore you will have this. All right, so that's a different formula, okay? Now, why do we need variance? As I said right in the beginning of this lecture, that it's digging more into how a population is behaving, or the values of X are behaving. Is it enough to know? Is it enough to know the average of some values of a population? Okay. For example, if let's take this example. Suppose you have two classes. Okay. In the first. In both the classes, you have students, okay? Let's just say that there are 3 students in both classes, and we've just had an exam where people have scored different marks. So in the first class, in the exam, 3 people have scored 3 marks, which is 79, 80, and 81 out of 100, let's say, okay? And x1 is the random variable which is measuring the mark of each student. Okay, so x1 takes these 3 values, 79, 80, and 81. In the next class, the 3 students have performed differently, and somebody got 70, somebody got an 80, and somebody got a 90. And x2 is a random variable measuring the marks of each student in the second class. Okay, now if you look at it, the average of both the classes is 80, of course, and that's very easy to understand. You have 79, 80, 81, which will give you the average 80. Similarly, a symmetric spread around 80. You can see that 70 and 90 around 80 will give you this 80. So the average of both the classes is 80. But clearly, if you look at the numbers, or how exactly, what exactly the numbers are, you can say that the numbers in the first class are more closely knit. They're more around the average. Okay, so there's more competition. If you think of it that way, okay, people are closer to the average. Whereas in the next one, the spread is more. Okay, somebody got a lot more. This person got a lot more than the average. This person got a lot less than the average than here. So the competition here is not as much, or is not as closely knit as this class, as you can see. So even though the averages of both the classes work out to be the same, we don't get a sense of how the marks are distributed in both the classes. Okay. And what variance does is it actually measures exactly that. Okay, so if you work out the variance of the first class by this formula, okay, because x1 and x2 both are discrete random variables. Okay, these are discrete values. If you work out variance of x1, you see the average is 80. So you have to take the difference of each value from 80 and then square it. So the first value, 79, the difference between 79 and 80, the first value is minus 1. The difference of the first value from the average is minus 1, because you put the value first and then the average. So 79 minus 80 is minus 1. And then you square it, multiplied by the PMF of the random variable, because there are 3 students, so they are equally likely to be picked. Okay, so the probability that you would pick the first student or the second student or the third student are all 1/3. Okay, so in this case, the probabilities, the PMF is 1/3 for each one. Okay, so the first one is this. Second one is the difference of 80 from 80 is 0. So that one gets a 0 square, or 0. Then the third value is 81 minus 80 is 1 square with 1/3 as probability. And you can see that this one is 0. This one will give you a plus 1. So these two will add up to give you 2/3, which is 0.6666. It continues. If you work out the variance of the second class, well, the difference of the first value from the average is minus 10 square. For this one, for the second one is again a 0. For the third one is a plus 10 square, and they will work out to give you this gives you 100. This also gives you 100. So that's 200 by 3, which is 66.666666, and it goes on. So you can see this value, the value of the variance for the second class is definitely much more than the value of is actually 100 times more. Okay, the value of the variance in the first class, which tells you that there is more variance. Okay, that's exactly what it is. It tells you that the spread in the second class is more. The value of the variance will, because this is more than this, the spread in the second class is more than the spread in the first class. And that's the work of the variance. And sometimes it's not enough to understand the population just by knowing the average. You have to understand, you have to figure out how much the values are spread over the population, and to understand them you have to find out the variance, and that's what it does exactly. Okay, variance gives you that idea. So one question is, why did we have to square it? If we just took the differences and multiplied by the PMFs, would we get the same answer? If we didn't square them, this would remain as -1, this would remain as +1, and this is 0. So the -1 and the +1 will cancel. So you will get a 0. So 0 variance, which would tell you that there is no spread in the class. In other words, everybody got the average mark, which is 80, which is wrong, because there is a spread. Somebody got less than the average, somebody got more than the average. So if we didn't square them, in other words, if we did not eliminate the minus signs, some of them will produce minus signs. If we did not eliminate the minus signs, there is a possibility that things will cancel and give you 0, which would mean there is no spread in the class, which is a wrong idea, because there is a spread in the class just from the values. You can see that. Okay, so the squaring is important here. Okay, so that's variance. And so because we are squaring the values, sometimes it's better to understand or to for the sake of units. We define what is called the standard deviation here, okay, where we take the positive square root of the variance. Because if you think about it, if we really wanted to figure out the spread in terms of, so here the units was marks, okay, somebody got 79 marks, somebody got 80 marks. So the unit, if you think of marks as a unit, the unit is marks, but the variance comes out in marks square, okay, because there's a difference between 2 marks, so marks square. So the units here is marks square. Okay, the probabilities don't have units. Okay, they are ratios. Okay, there are no units in probabilities. So the variance has marks square. But if you really want to find out the spread in terms of marks, because you started with the values as marks, okay, then you take the positive square root. And so the units will get reduced to, instead of marks square, you now have marks again. So standard deviation is basically telling you that you standardize the units. Okay. The squaring was important to eliminate minus signs, but to bring the units down, you have to take the square root now. So standard deviation gives you that. Okay. It doesn't serve any extra purpose. It also tells you the spread, because if you square root both sides, this square root will still be more than this square root. So this spread will still be more than this spread, which is correct. But it's in standard units now. It's the same units as the marks which we started with. Okay, so that's why we need standard deviation. Okay, all right. So now we come to some properties of variance. Okay. So first of all, the first property that we need to look at is if you have a constant random variable, okay, then the variance will be 0, because if it's constant, if it's a constant random variable, it means that the average is constant. In other words, if the random variable takes only the value b, then the average will also be b. So there will be no differences. Okay, no difference between an individual value and the average value, because they're all the same. So the spread is 0, and if you just put things here, you will understand, because each value is b, the average is also b, so all of them will be 0, and you will get a 0. What about if you multiply a random variable by a constant a? Well, just looking at this formula, you can see that a square will come out. If you multiply a random variable by a, each of its values will get multiplied by a. So the average will get multiplied by a. So instead of m, you will have a square m square. And so let's just do this. Okay, we can do this very quickly. I don't need this example anymore. So this is what it is, okay? So expectation of this one, instead of x squared, I now need, this is the new random variable whose variance I want to find. So this is ax whole square, okay? Minus, so that I'm finding out the variance of this. So variance of ax is this, okay? Minus, well, the average will be, if the average of x is m, the average of ax is am, because you can take out a, because it's constant. So this will be, so the average square will be a square m square. Average of ax, remember, that's whose variance we're trying to find. Yeah, and this of course is a square x square. You can take out the a square from here. You can take out the a square from here. So you're left with expectation of x square minus m square, right? And that's just variance of x. A square variance of x. Okay, so that's again very simple. Okay, just following the formula. Next we come to, what if you add two random variables? The first one has expectation m, in other words average value is m. Suppose the second one has the average value n. In that case, you get variance of x plus variance of y plus an extra quantity here, okay? They're not linear. If this quantity was not there, this would be linear, okay? Remember, just like expectation, you could just take out, you could just, add the separate variances. That property is a very nice property to have always, linearity, but that's not true because you have a different quantity here. You can actually see that if you try to do this, remember what would be the expectation of x plus y? The expectation of x plus y will be the expectation of x plus expectation of y, and so that would be m plus n. Okay, n is the expectation of y. So if I want to find the variance of this, if I want to find the variance of x plus y, I need to find the expectation of this new random variable minus the average of this random variable, which is m plus n, and then square the whole thing. That's what I had to do. Okay. Now, if you think about it, or if you just simplify this, inside this thing, this is, you can write this as x minus m plus y minus n, and the whole thing square. Right? I'm just taking m with x and n with y. Okay. The outside you have a square. And this would be, well, if you just square them, you would have x minus m square plus y minus n square plus 2 times x minus m and a y minus n, right? And by linearity, you would have expectation of x minus m square, which is variance of x, plus expectation of y minus n square, which is variance of y, plus 2 times expectation of this new quantity, x minus m y minus n. This quantity, expectation of x minus m y minus n, is written as the covariance of x and y, covariance between x and y, whichever way you want to call it. Okay, so if you do the variance of x plus y, you get variance of x plus variance of y plus 2 times this quantity, which we call the covariance of x and y. Remember, if y was x, if they're the same, then you would have x minus m again, so x minus m whole square, which would be variance. So covariance, I'll just switch to a better pen. covariance of x with x is expectation of x minus m twice multiplied here, x minus m square, which is the variance of x. Okay, so variance is itself, it's actually the covariance of x with itself, but covariance of x with y is expectation of this quantity. Okay, all right. So this is, so it's not linear except for this quantity. Now, if the covariance is 0, in that case the variance is linear. Okay. Now the covariance is 0 at one particular time. Okay, when the two random variables x and y are independent of each other. So this covariance can be actually written like this as well. Okay, this is another formula for covariance. Okay, if you multiply things here, you can easily see that this formula can be written like this as well. So let's just do that quickly. Expectation of if I multiply this together, x with y, and then x with minus n, then minus m with y, and then m and n, or minus m and minus n, so you get a plus mn. Again, by linearity of expectation, you can just take this expectation of the individual things. So you would get expectation of xy from the first term. You would get minus n times expectation of x, which is m, then minus m times expectation of y, which is n, these two are same, plus expectation of a constant quantity, which is mn. So one of them will cancel, this one and this one will cancel, for example, and you're left with expectation of xy minus mn. Okay, so if you just simplify this, it becomes again a simpler formula, just like this. Okay, and you can see if y is x, you get x squared, then n becomes m, you have m squared. So it follows the same pattern there. Okay, so the covariance can be written in a more concise formula like this as well. Okay, so now it turns out that if x and y are independent, then expectation of a product of two random variables is the product of the individual expectations. So expectation of xy in this case, when they're independent, will be expectation of x times expectation of y. We've learnt this. But expectation of x is m and expectation of y is n. So if the two are independent, x and y are independent, in that case you would get mn, because this becomes mn, minus mn, and that's 0. So the covariance of x and y becomes 0 if x and y are independent. I hope that's clear, okay? Because these two can be written into as this product, and that would be mn minus mn, so 0. So the one time when this variance acts like a linear function on x and y is when the two random variables are independent of each other. In that case, the covariance is 0, so this quantity vanishes, and so you have a very simple linear formula of variance of x plus y equals variance of x plus variance of y. Okay, so let me just write that down. Variance of x plus y will be equal to variance of x plus variance of y if x and y are independent. I think we can put that in as a number 4 here. Okay, it's a special case of number 3. Okay, so these are some of the properties of variance. Okay, with that, I think let's just work out very quickly variances of a few known distributions. and I think we'll get an idea of what exactly it is doing, and then how to find the variance of different things. So we'll just do that. We'll find out the variance of a few standard random variable or discrete distributions, and we'll get an idea of how to do them. So one of the first and the easiest ones is, what if you have a Bernoulli trial, okay? What's the expectation of a random variable which is a Bernoulli trial? Let me call that I. So I is a Bernoulli trial. It's like an indicator. It takes 1 and 0 as two values, like an indicator random variable. So it has success with probability P and has failure with probability 0. I mean, sorry, not 0. So I takes 1 or failure with probability P, okay, and takes the value 0 or failure with probability 1 minus P, which is written as Q sometimes. What's the variance of this? Okay, if I want to find the variance of this random variable, which is a Bernoulli P trial, well, that would be, if I use the second formula for expectation, that would be expectation of I square minus the average. Now, the average of a Bernoulli trial is P, whatever the probability of the success is. So M in the previous formula becomes P here, so you get a P square, okay? Now, if you think about it, I square is actually I, because I takes two values, 0 and 1. If it takes the value 1, 1 square is 1. And if it takes the value 0, 0 square is also 0, okay? So in other words, spectrum, what is the spectrum of I? It's 0 and 1. What's the spectrum of I square? It's 0 and 1 again, because 0 square is 0, 1 square is 1. So I square takes the same values as I, okay? And therefore, the two random variables are actually equal, okay? I square is nothing different. So this really is the same as expectation of I itself, because I square is I. Minus P. And what is P square, sorry. What is expectation of I? It is P. So P minus P square. And that's the variance of I, okay? That's the first variance that we have found, okay? If I is a Bernoulli P trial, its variance is P minus P square. If you want to find the standard deviation, of course, you just take the positive square root, so you get root of P minus P square. That's the standard deviation, okay? What if a random variable is a binomial random variable with parameters n and p? What's the variance of x? Well, x, as we know already, and we've done it many times, x can be written as the Bernoulli, as a summation of n Bernoulli trials. And each of them are Bernoulli trials with probability p, because they share the same parameter here. And they are IIDs, in other words, independent and identically distributed. So if I want to take the variance of x, I take the variance of I1 plus I2 plus up to In. But now the good thing is they're all independent because they are IIDs. And independent means there will be no covariance. Okay? The covariance is gone. So in other words, variance acts like a linear function when the individual random variables are all independent of each other. So this will be variance of I1 plus variance of I2 plus variance of I3, like that, okay, up to variance of In. But each of them are Bernoulli P trials, so each of them will have the same variance which we have just found. The variance of each I will be this. So that will be n times this thing, p minus p square. That's the variance. You can take out one p, then you have np 1 minus p. In other words, sometimes it's written as npq. That's the variance of a binomial distribution. Okay, it becomes very easy because you're dealing with independent random variables and independent Bernoulli trials. Okay, what about, let's do a final one. What about x is a Poisson distribution with parameter mu? What's the variance in this case? Well, or let's write y. Now you know there are two ways to think about it. Either go by the formula, or there's another way of thinking of Poisson distribution as a limiting case of the binomial distribution. Remember that if x is a binomial distribution, in other words, x is like this, it becomes a Poisson distribution when this n becomes big, but p becomes small, such that the product is a constant. Okay, this was the condition, and this was there in the assignment problem, and we've worked it out as a solution, and we've understood it. So a binomial distribution starts to behave like a Poisson distribution when n and p, in the limiting case, when n and p behave like this. Okay. So if you think about it, now if you take the variance, so variance of x should converge to variance of y. If x converges to y in this case, then variance of x should converge to variance of y in this case. But variance of x is what? It's this. It's n p 1 minus p. Okay? But that's np is mu, and 1 minus p is mu over n, right? From this relation, p is mu over n. But this is when n is very big. In other words, n goes to infinity. In the case that n goes to infinity, this quantity becomes 0. Okay, n is in the denominator, that becomes infinity. So this is 0. So this tends to mu when n tends to infinity. Okay, so therefore, in this condition, when this is happening, in other words, when n is so big, the variance of x becomes mu, which then becomes variance of y, and so variance of y is actually mu. Okay, that's an argument from limits. Okay, I hope that's clear. In this particular condition, the variance of x becomes mu, because if you write it out and take n to be infinity, you get mu. The variance of x becomes mu in this condition. But variance of x should also converge to variance of y because x converges to y. So by that argument, variance of y should be mu. Okay, so all of this put together, you have variance of y, which is a Poisson distribution, as mu. So the variance of y is mu, variance of a Poisson distribution is mu, even the expectation of a Poisson distribution is mu. Okay, you can think of this, if you're not satisfied with this limiting argument, you can also use the formula and work this out. So if you think about it, if I want to find variance of y by the formula that we're using, y square, expectation of y square minus the expectation square, mu square. Okay, I just need to find out what this is and I will be done. Okay, I just have to subtract mu square from that and I will be done. So let's figure out what is expectation of y square. We've just worked out before. This formula will be, because this is discrete, Poisson distribution is discrete distribution, y will take values. So if y is a Poisson distribution, what's the spectrum of y? The spectrum of y is 0, 1, 2, goes up to infinity. So you will have y takes these values. Let's take k. Each value is k, okay. In other words, k is one of them. So I have y square, which is k square. K will range from 0 to infinity because the summation must range over the entire spectrum of y. And by Lotus, in other words, law of the unconscious statistician, I don't have to think about what is the expectation, what is the PMF of y and y square, which is this new random variable. I just write the PMF of y, which I know. It's Poisson. What's the PMF of y? It's e to the minus mu, mu to the k over k factorial. Okay, so I don't have to figure out what's the PMF of this new random variable y square. I just write down the random variable of y. Okay, let's just work this out. So this will be, if I substitute this for this, remember, e to the minus mu is a constant. It has nothing to do with k over which the summation is happening. I can take that out. So I will have e to the minus mu. Inside the summation, which is from 0 to infinity, I will have this k square over k factorial mu to the k. This is the quantity I need to figure out, and I will be done. So let's find out what this quantity is. Just this quantity, okay? Well, we know one thing. E to the mu is summation k from 0 to infinity 1 over k factorial mu to the k. That's a standard formula for the exponential of mu. Okay. Now, I need k's here, so I need to differentiate both sides with respect to mu. So I will get if I differentiate e to the mu with respect to mu, I get e to the mu itself. If I differentiate this with respect to k, I will get a k with a k factorial, okay, and mu to the k minus 1, and the summation will happen from, well, it can happen from 0 itself. Okay. All right. So is this? Not yet. I need another k. But for another k, I need to differentiate it once more. But I have a k minus 1. If I differentiate it now, I will get a k minus 1, which is not what I want. If I need a k here, which then if I differentiate, I will get the k squared. So let's multiply. This is differentiating with respect to mu, this step. Okay. Let's multiply by mu on both sides. The one mu multiplies on every mu to the k minus 1 and gets you mu to the k. Now let's differentiate it once more. Let's differentiate this once more with respect to mu. What you get from the left hand side is, let's differentiate this once with respect to this one. In other words, differentiate the first function. I get e to the mu, and then I differentiate this, so I get mu, e to the mu, which is common, so I get 1 plus mu here. Okay, so this is differentiating the left hand side with respect to mu. Let's differentiate this once more with respect to mu. I will get summation k from 0 to infinity. Now I'll get k squared because this k will come down. K factorial mu to the k minus 1 again, but I'm looking for this sum where you have k, so I need to furnish this mu once more. I need to multiply mu once more, and now I have this quantity. They're the same. So this quantity is this quantity. Okay, so let's just do that here, from here. Therefore, this will be, if I multiply e to the minus mu to this quantity, e to the minus mu will multiply e to the mu to give you 1. So you will be left with mu 1 plus mu, mu with 1 plus mu, and that's mu plus mu squared. So this thing, this e to the, or expectation of y squared, this quantity, all of this gives you this. That's expectation of y squared. So therefore I needed variance variance of y will just be this minus mu square. So this thing minus mu square is mu, which is what we got before. So variance is mu again, okay? So you can either figure out the variance of this Poisson distribution through this limiting case, or actually figure it out by the formulas, and they will be the same. There are more, there are other discrete distributions which we have done, for example, hypergeometric, geometric, negative binomial, first success distribution, all of them. So you can, actually find out the variances of all of those cases, okay, either by a logic like this, or using the formula, and that'll be a good exercise, okay? So I think we will finish this here, and that's more or less what you need to know about variance, okay? We'll take things forward in the next lecture again. Thank you.